We defined customer requirements as being directional and qualitative. The intent was to have a simple means of capturing customer needs without getting bogged down in the details. To develop our customer requirements, we leveraged the entire group. First, we explained the definition above of a customer requirement. Then we had a first round where everybody was free to submit ideas for customer requirements. After that, we had a second round where everybody voted on the strength of all the submitted requirements and ranked them and gave them classifications of either a hard requirement or a goal. The overall result was 31 requirements developed into the customer requirement stage. Next, we'll go over 3 examples. The first example is that of output power, which had the 11th ranking of the 31 and was classified as a goal. Specifically, the description is, the product shall be capable of charging most devices while they are in use. A net positive power shall be provided to most devices even when they are using power, such that the device will have increased battery charge while being used. Notice how this speaks of the general ability to provide power, but doesn't give a quantitative amount of power. Another example is requirement 17, waterproof electronics, which was also classified as a goal. The device must be able to withstand an unexpected encounter with a puddle. The last customer requirement example is noise control, which had a rank of 18 and was classified as a goal. The description says, the product should be as quiet as possible and should not emit annoying noises. You can see that there's a lot of work here to change this into the qualitative statement into a quantitative sound requirement, but it does capture the essence of what customers would want to see.
After ranking our customer level requirements, we then went on to expand them into product level requirements. A product level requirement narrows the broad customer level requirement into specific quantifiable constraints that will drive the work of the design and analysis teams. To determine these constraints, research must be done, such as comparing with similar products on the market, like shoes in general, for weight and size requirements, as well as industry and professional society standards like those of the International Electrotechnical Commission. I'll now go through a few examples to show the thought process of turning a customer requirement into a product level requirement. First, let's look at the necessary power generation for this device. We have concluded that the hydroelectric shoe must provide at least 130 milliwatts of continuous power. But where did this come from? We first looked at the charging needs of the mobile device market, one of our target uses. Smartphones hold 23% of the market share and were identified as the heaviest power consumer of the bunch. Your average smartphone, under constant audio playback, has a battery life of 40 hours while providing 3.7 volts and 1.4 amp hours of current. Simple calculations then show the average power being produced is 130 milliwatts. Next, we'll use a societal standard to determine what is necessary for waterproofing our electrical components. In order to meet IEC standards for water submersion, we must adhere to code 60529 IPX7. The first part of the code refers to device protection against intrusion of solids and liquids into the electrical enclosure. Our particular interest is the final number 7, which refers to protection from complete submersion in water. To meet this standard, the device must withstand immersion in water at 1 meter depth for 30 minutes. By meeting societal standards, we can ensure customer safety and product approval. Finally, we'll look at a slightly more abstract requirement. It can be difficult to say what is too noisy and what isn't for a device. We have therefore set sound pressure level maximums to quantify noise generated by our product. While walking, our device must not generate more than 40 dB, which is equivalent to a quiet library, and while running it must not exceed 60 dB, which is equivalent to conversational speech. After developing all of our product level requirements, we were ready to pass these on to the design team. We presented them with 31 ranked and organized requirements, thoroughly researched and explained. We then settled into a support role to interface with the design and analysis teams to answer any questions that would arise. Let's move on to the design team.
Hi, my name's Ryan Moore, and I'm going to be going over the design team portion of a product realization project that involved converting a hydroelectric shoe idea into reality. This agenda shows what I'll be covering. I'm going to first talk about the design team's place not only within the product realization process, but also our subgroups' place within the overall team. Then I'm going to discuss the development of our to-do list that really went from generic tasks all the way to itemized list of specified deliverables that would be completed by responsible members. Then I'll discuss deliverables, which goes all the way from understanding customer inputs to generating a bill of materials with corresponding suppliers and costs, as well as a final CAD model, and what helped us along the way. First section is our place within A4. Paul and Bytes' product realization process consists of 4 phases. We initially thought our design team would remain within phase 2, but we found out that our top left to bottom right Gantt chart eventually evolved into a vertical simultaneous task completion molded together collaboration project, and we ended up spilling into phase 2, 3, and 4. Our team consisted of about 10 members. We're one of the bigger teams, and we had members on other teams which aided that continuous flow I was talking about earlier. The overall team was about 30 people, or pool of students. To develop our to-do list, we first created this initial Gantt, and we thought we were going to stay I already mentioned that we were going to do most tasks within the concept phase, but it made sense to take ownership and start picking up tasks in other phases because it was a one-man job, didn't need to be completed by 2 people. This slide shows an example of one of our to-do lists that we went over each meeting. We had project rhythm updates where we'd roundtable and each member would tell us what's going on with their part and if they were going to hit certain deadlines. So although our Paul and Bytes drove the generation of these tasks, we did take into account each member's interests, their core competencies, and their other memberships in order to assign tasks. This final Gantt chart just shows the design team's place within all the different tasks, and this Gantt chart was actually 3 pages long. I'm just showing one here. But our sequence was rearranged. There wasn't a series. Well, we tried to make a series of handoffs as best we could, but it was more vertical than originally anticipated. Now on to deliverables. It took a while or significant time to fully understand all of our user requirements and customer inputs. This was a handoff from the user input team, and it compiled a lot of data from everybody in our pool of 30 students, and we began to filter these, start eliminating personal preferences or those subjective functions, and change qualitative data into more quantitative statements, and start throwing out those that weren't core or essential to the problem. We ended up with these 5 functions here, and in sentence form, our goal is a shoe needs to be designed which can comfortably support the user's foot and generate electricity while being worn. Additionally, the shoe must be able to transfer the generated power to a variety of electronic devices. Function structure, although it might look a little busy at first, you can see after quickly glancing at the key that it's pretty simple. You've got your energy, material, and signals flowing into the left. They're conserved and flowing out on the right. The overall function shown in yellow, is accomplished by sub-functions and sub-sub-functions in peach and kind of light blue or aqua, respectively. We did leverage previous work when creating this, and even gave our fresh take on it before looking at that old work to not taint our creation process. We ended up with this comprehensive structure. Problem setup was a good example that not all deliverables turn out the way you want. They're not going to all be high benefit, low cost. This one fizzled out. It was preemptive. We were double working with analysis, so we decided to drop it and better use our resources. We just didn't have enough understanding at this point, and it would come with time and more analysis. This slide, I'll take a little time on it. The right matrix that you see here, far left column has different solutions or functions. Each adjacent column to the right of the far left has different methods of accomplishing that function. So for instance, to convert pressure to fluid flow, you can either do that with water, with a glycerin solution, an alcohol solution. A key point to mention here is what's highlighted or outlined in red is our final concept. So those are the ways, the methods, the means we chose to accomplish the function. And we chose this primarily based on feasibility, practicality, and whether our solution was readily available or not. So in the example I mentioned earlier, water, it's something that it's very easy to come by. There's a lot of data available on it, and it doesn't have those compatibility issues like glycerin and alcohol, so we went with that. The left two screenshots is just an extraction from our report that shows a little bit of elaboration on each of the methods. So we did take time to evaluate every single proposed solution to each function. Our CAD model was created by two members on our team who were very experienced in CAD, well, in my opinion. And if I could summarize it in 3 steps, it would be generating these surfaces, applying a three-dimensional coordinate system, passing a surface over it. And you really want to start simple in this case and start adding that complexity. So, yeah, you first generate the surface and create the main shoe, then start building the components, and then assemble those all together. Well, that sounds really simple, but look at the comic strip on the top or the bottom left of this slide that shows a sequence of screenshots of how this model was developed over time. So like these bullet points mention, yeah, start with a few components, model them, and throw it all together and add the finishing touches to polish it off. Final deliverable was the bill of materials, and this is one of those that spilled over into the other product realization phases, and it made sense to just identify suppliers, build the bill of materials, and estimate the cost all at once. A lot of the components were readily available on large distributor websites like McMaster-Carr or Grainger. It's only a matter of filtering results and knowing what you're looking for, having some experience with those sites in order to get to what you needed. A few of the items, like the micro hydroelectric power generator, small high-performance check valves, and the micro USB hookup, took a little more experience, took a little more digging to find. When you throw it all together, this shoe cost around $370. You can see the final total here includes labor and assembly. We found that large quantities would discount this total to about $350. Still pretty pricey, but it's very accurate bill of materials. With that, I'll conclude my section, or the design team's portion of the video, and pass on to the design or the analysis team. Thanks for your time.